Riggan. This is our work on thermal divisible synthesis of face images using multiple regions. This is a collaboration with my colleagues Nathan, Shuowen, and Chan Hu. So the main objective here is we want to be able to take thermal data. This could be conventional thermal, polymetric thermal faces, and then synthesize a face such that we could end up using this type of imagery in conjunction with existing face recognition models. You know, this could be embedding, this could be landmark detections, this could be, you know, your traditional VGG face, any type of facial recognition software that you could think of. And the main idea here is we want to be able to perform face recognition at nighttime in low light conditions. And the other purpose for this is when analysts are returned a lot of matches in facial recognition software, they have to verify or adjudicate those matches somehow. So with a customized approach, they wouldn't necessarily have a way to visualize what the system's actually doing. So that's where the synthesis approach comes in. So in this paper, we exploited a multi-region synthesis approach. So here we're using both global and local features, and then we put them through a mapping. It mapped the thermal data to the visible for each region, and then leverage all of that information to perform one holistic synthesis. So the main idea, the main thing that we do here is we set up a joint optimization across all these regions. We leverage weighting, appropriate weighting for each of the regions, the eyes, the nose, the mouth, and then the entire face. And so what kind of goes into this optimization is just the minimum error between the mapped visible representation and the mapped thermal representation. And then we add some regularization constraints in there, such as the alpha norm and total variation. And so in the end, what we get is something like this that kind of looks like it's not quite a visible face, but it's not a thermal face either. We end up enhancing a lot of the fiducial details, particularly around the eyes, the nose, and the mouth. So here's just a wide overview of some of our results. So on the top row, you see the conventional thermal. The next row down is the visible ground truth. And then we have two other synthesized results, one using polymetric thermal and one using conventional thermal. And so one thing you can notice here is that the polarimetric thermal adds some additional information, particularly around areas around the mouth, and so you get enhanced details in the reconstructions. The other thing you can compare our results with are a recent result presented at IJCB this past year, and so this figure here on the right, you can see the ground truth visible, the conventional thermal, and then you can see the results from the IJCB paper, which look very photorealistic, but yet they're not very discriminative. It doesn't actually correspond to that person. In fact, this looks more like another person in the data set that's not shown here. So it sort of brought up this interesting question with the GAN-based approach. It automatically went to the photorealism more than the discriminability. And then we ended up comparing the recognition result, or the face verification results, which are shown here, and the multi-region synthesis ended up on top. The other thing we did was a big challenge in face recognition is the registration of the faces. So with thermal data, you'd have to create a custom landmark detection algorithm in order to register these faces. Here we end up synthesizing the faces first and then applying out-of-the-box landmark detection software. And so again, you can see the results on both the conventional thermal and the polymetric compared to the visible. And here's just some references. So if you have any questions, please stop by our poster. And we're also going to have a demo of this running real time. So please stop by.